Hi, welcome to a new video. In this lecture, we're going to talk about classification problems. So this is a supervised learning problem. Now, what is a classification problem? The idea here is that we want to make a model, we want to predict a categorical variable. That's the difference between regression and classification. In the regression model, like in this example, here we have two variables, the size of the animal, and we want to predict the speed of the animal. Right? So if you notice, our y variable, the dependent variable, it's numeric. Therefore, that's a regression problem. Now, in the case of classification, it's when you want to predict something that is categorical. For example, here, our dependent variable is whether the observation is a dog or a cat. Therefore, that's how we want to separate them, we want to classify them. So the prediction is not numeric, it's categorical. In both cases, regression and classification, we have some independent variable, x variables, and they can be either numeric or categorical, but the difference is in the dependent variable, the y variable, the one that you want to predict. There are different type of classification problems. For example, the binary classification is when we have two possible outcomes, when our y variable has two possible outcomes. For example, in spam detection, so two possibilities are that the email is spam or not, right? So that's binary. Fraud detection, if let's say that we are analyzing some transactions for a financial institution, then the two possible outcomes in that scenario, it's like whether the transaction is fraud or not. Now, if there are more than two possibilities, let's say three or more, then that's what we call multi-class classification. So here, each observation, the outcome or the output, it may have three or more possible values. Let's say that we are classifying a plant or animal species, so there are multiple options for just one individual, for one creature. There are multiple possibilities. So that's what we call multi-class classification. Let's say that you are trying to predict the quality of a product or in a manufacturing company, based on some variables. Then maybe there are, like three levels, like bad quality, medium quality, or good quality. So that's another example of a multi-class classification. Multi-label classification, it looks similar initially to the multi-class, but they are different. So multi-label means that in a single observation, it is possible to have two or more classifications. So, for example, if we are analyzing, let's say, crops, for each plant, we take a picture, right? So it is possible that a single plant may have multiple diseases. That's a possibility, right? There in different parts of the plant. So it has multiple labels, not just one. Because if it adds one, it means that, okay, there are multiple options of disease, but it can have only one. But it is possible that the same plant will have two or more. So let me show you a more graphical example on how this looks. So in the binary, there are two classes, right? We want to separate them based on some features or independent variables, here x1 and x2. The multi-class classification, there are three different classes or more, right? They have different shapes, and we want to find a way to separate them. This is multi-class. So multi-class is each frame here, each square is just one observation. If you notice, it has a single value. There are three possibilities, but there is only one value, right? This is for the three observations. Now, you have multi-label when a single observation may have two or more labels. That's a possible. For example, here, the first observation, there are two labels, right? We have two different objects. In the second observation, there is just one, but in the third observation, there are three, right? So there are three labels. There are three labels. So that's multi-label. And the problem can be multi-level and multi-class, of course, right? The combination of these two. All right, so that's the classification problem. Remember, one thing is the problem, and a different one is, okay, how you solve that problem. So for classification, we have different algorithms. So some of them are similar to the regression problem, like similar algorithms, but they are, of course, adapted to the context. So we have KNN, the k-near neighbors. We also have a logistic regression, which we're going to discuss in this video. This is like I would say, for regression, you have linear regression, which is the most popular algorithm. So in classification, the logistic regression for sure is the most popular algorithm. There are other alternatives such as trees, random forests, support vector machines, SVMs, XGBoost, and neural networks. So these are different ways to solve the classification problem. Okay, so let's talk about the logistic regression. So in this case, and this is important, this is the shape, or this is how it looks, the model. So it's not linear compared to the linear regression. So please notice here that the variables are in the denominator, right? And they are in an export here. All right. So the first thing that you should know is that the outcome in these models is a probability. That's what you get. When you plug in the values of the variables, once you have trained the model, and then for any observation, you replace x1, x2, the features for the observation, what you get is a probability. And that probability is that y is equal to 1. Or that's the probability that that observation belongs to a specific class. So typically, for example, for one, if you're analyzing whether a person has a disease or not, so equal to 1 means that the person has the disease. If you're analyzing transactions, so maybe 1 is when there is a fraud in the transaction. So yeah, this is, you get here the probability. Let me give you an idea to kind of like show you how it works. Let's say that we want to create a model to predict whether a student is going to pass or not a specific class. Let's say machine learning, the machine learning class. So you need to collect data, right? Because it's supervised learning, and you need, of course, the data. You need labels. That means you need Y. So some of possible variables, let's say x1 is, I don't know, like attendance, the percentage of attendance. That has to be important, right? There is a second variable, is the hours per week that the student does some like independent study, hours per week, right? And then you can keep adding more variables if you want. There is a big one here, the GPA for sure, like before the GPA before the student begins the class. You can keep adding the variables, and then of course you need the label, right? Why? And this is whether the student passes or not the class. So there are two options. Let's say P for pass, the student is passing the class, or F if the student fails the class. There are other options, of course, it's dropping, but that's fine. Let's say this is a binary problem. So you need to get some data. So percentage of attendance, let's say we have a good student. So this is 100%, hours per week, let's say 4 hours per week. That's on average. GPA, 4, like perfect GPA. In the past, the student passed the class, right? So you need to keep adding, more observations, and you need both cases, students that pass the class and students that fail the class. Because of course, if you want your algorithm to learn, you need to show the algorithms the different cases. So let's add another student. Let's say that this one, the attendance is not good, 40%, hours per week, 0.2, GPA 3.3, and that specific student didn't pass the class, right? So you keep going with the table until you have, like a good number of observations. So when you train the model, this is what you get, this equation here. You get the betas from that equation. That's what you compute. And then when you add like a new observation and you plug in the new observation, the x values into this equation, what you get is a probability. So let's say that someone similar to the first student, that probability, these numbers are just arbitrary numbers. So I'm going to say that this is 0.85. That's the probability that y is equal to 1, or that the student is going to pass the class. It makes sense, if it has good attendance, a good, independent study, high GPA. So most likely a student is going to pass. But if then you have someone that is not showing to the class, few hours per week of independent study, low GPA, then maybe the probability is lower, right? That will depend on the class, of course. So let's say 0.15. So this is what you get from the logistic regression model. This probability is an estimation, right, of the probability that the student is going to pass the class. So now how can you translate the probability to a prediction? So this is what we call y hat. So y is the real value, y hat is prediction. Y hat is prediction. So how can we go from probability again to a y hat, which is a prediction? So typically, what we do is we need a threshold. So let's call it theta. And that threshold, I'm going to use an arbitrary threshold of 0.5. So what is the meaning of this? So if the probability is greater than 0.5, then I'm going to assume that it's high, it's closer to 1. Then my prediction is that that student is going to pass, right? Because I'm saying that the probability it's closer to 1, greater than 0.5. But if it's less equal than 0.5, then my prediction, my y hat, is that the student is going to fail. That's the classification. So to make classifications, I will estimate the probabilities first with the model, right? And then you need to define a threshold. On the threshold, you will be able to make the prediction to find y hat, right? So most of the classification algorithms, they work this way. You need a threshold. Typically, they will assume 0.5, but again, that's not always the best possible threshold. And there are some algorithms that they don't find the probability. They just compute the y hat directly. For example, the SVM, support vector machine, that algorithm specifically, they don't give you that. It doesn't give you the probability. You get the y hat directly. Okay, so let me just mention a couple of things more about the logistic regression. It has a shape of the letter S, an S curve, which is here, and it's bounded between 0 and 1. So regardless the value of x, the output is going to be a probability between 0 and 1. That's not the case of the linear regression. That's not possible for the linear regression. It's unbounded. But in the case of the logistic regression, it's bounded. It's going to be between 0 and 1. And this is the threshold that we were talking about. All right. So once you are able to make predictions, y hats, we need to be able to measure how good is our model. So in order to do so, you need to find the confusion matrix. This is the standard way to analyze the performance of a classification algorithm. Now, you gotta be careful because in some cases, depending on the software, some packages will give you the confusion matrix in different order. So in this one, you have the actual class in the rows. Actual or real means y. So you have the observed value, the real data. And then in the columns, you have the predicted class. So that's y hat. So that's what your model is suggesting. That's the prediction. So positive typically means 1. So if it's predicting spam, so that's your class 1 equal to 1 is spam. And negative is 0, right? No non-spam. If it's fraud, this is fraud equal to 1, then a normal transaction is going to be equal to 0. But at the end of the day, that's up to you, right? What you define as positive and negative. What matters is that you are consistent. So just be careful. So once you say, okay, this is my 1, this class is equal to 1, that's like a label encoding right there. Then you need to stick to that encoding. All right. So we can measure different variables or metrics in these confusion metrics. So in this position, we get the true positive. That means that observations that are here, that means that our model predicted that it was equal to 1, and effectively that observation was equal to 1. So this is correct. Same idea with the true negative. So in this case, our model said that it's equal to 0 or negative, and in real life, the y value is equal to 0 or negative. So this also, we are right. So this diagonal will give you the observations that your model classified correctly. And that's how we measure the accuracy that you see right here. The accuracy is just the percentage of observations that were classified correctly. So it's true positive plus true negative divided by the sum of all of the observations, right? So it's the diagonal. Now, the accuracy is an important metric, but you gotta be careful because in some cases it's not enough to have the accuracy. That's why we have here more metrics, such as the sensitivity, specificity, and the precisions. What are these? So sensitivity and specificity, these two metrics, they measure how good is the model for each class, for the positive and for the negative. Sensitivity, for example, is for the positive cases, from the total positive cases, how many were classified correctly in a percentage metric. So it's true positive over true positive plus the false negative. So this row, if you add this up, that will give you, like all positive observations in your data set, right? So true positive divided by that sum will give you, okay, how many of those our model got right. Now, similar idea with the specificity. It measures a percentage of how many of the negative class or the zeros were classified correctly, right? So it measures using the real value, the actual value, the y. Here using the rows. Now, in general, when we have binary classification, we call them sensitivity and specificity. But if you add more classes, like 3 classes, 4 classes, now you cannot call them like that. So I prefer, and it's a little bit more practical. And in machine learning, it's common to call these two metrics as recall, the recall. The recall. So the recall for the class of the positives or for equal to 1, and the recall for the negative or when the observation is equal to 0. So the recall is just like the percentage of observations that were classified correctly for that class. That's the interpretation of the recall. It gives you an idea of how many were classified correctly in a percentage metric. Now, a second important metric that you need to consider here, it's called the precision. So the precision measures the quality of the prediction. It's like how much you can trust your model. So the precision is, because please notice that here we analyze the column and we use the predicted classes. So for the positive, for example, here, we're saying, okay, this column, the sum of these refers to observation that our model predicted as positive, right? So how many of them were classified correctly? So that's true positive divided by the sum of this column, right? So that gives you, okay, how much you can trust your model, right? That's a quality metric. It measures the predictive capability of your model. Same idea with the negative. So you can measure the precision for the positive and the precision for the negative. It has different name here, but again, you can call them precisions for one class and for the other, and recall for one class and the other, or just sensitivity and specificity, which again, it only makes sense when this is a binary classification. If you have 3 or more classes, then just call them recall, and that's it. Let's check an example here, numerical example. So this is for the spam classification problem. We have 2 classes, binary problem, right? We create our model, we define a threshold, and then we've computed our predictions. And now we're trying to assess how good is the model. So the 600 here means that that's the true positive. So this is observations that were classified correctly as spam, and they were spam. The 9,000 refers to emails or observations that were labeled as or predict. The model said they are non-spam. Effectively, they were non-spam. So in this diagonal, it's fine. So you can measure the accuracy here. It's gonna be our accuracy in that specific in this problem will be 9,000 plus 600 divided by the whole table, right? Like 600 plus 300 plus 100 plus 9,000. So that's going to give you the accuracy. And now you can compute recalls. Remember precision and sensitivity. So the recall, I'm going to find both sensitivity and specificity. So for the first one, for the positive or when it's equal to 1, it's going to be equal to 600, right? I analyzed the actual values. That's what I'm looking at the rows because I have the actual values. So in our data set, there were 900 spam emails. So our model got correct 600 out of 900, out of 600 plus 300. So that's the recall for that class, which is equal to 0.66. It's small. It's not that good. 0.66. And now for the specificity of recall for the non-spam is 9,000 divided by 9,000 plus 100. Again, we're looking at the row. We're looking at the real values. We're looking at the y, not the y hat. Y hat is prediction, y is observed values. Like what really happened. Okay, so this probability is 0.98, is high. So what is the interpretation of this? So in the case of the recall of spam, we're classifying correctly 66% of the spam emails. And in the case of the non-spam emails, we're classifying correctly 98%. That's the interpretation of this. It measures from the observations how good was the model for each class, like how many classified correctly, again measured as a percentage. And now, similar idea with the precision, but now we measure the quality. So the precision. So we're going to find the precision for the two of them, for the positive cases, for the negative cases. So for the positive cases, it's going to be equal to 600. Now we look at the column. Because in the columns, we have the prediction, y hat, predicted, right? Y hat. So our model predicted 700, right? 700 spams, but it got right only 600. So the precision is 600 divided by 600 plus 100. Again, this is a measure of quality. So how much you should believe the predictions from that model. This is 0.85. So this one has a good precision, but the accuracy is not good for that class, right? And then for the zeros or non-spam, is 9,000. Again, we look at the column, divided by 9,000 plus 300. So we get good quality for this one too, good precision. All right, so here it needs improvement of the accuracy of the recall of the spam is not good. Actually, if you measure the accuracy here is high. The accuracy is high because you have 10,000 emails and 9,600 of them were classified correctly. So your accuracy, it's high, like 96%. But the accuracy as a aggregated metric, it doesn't show the complete picture. And the complete picture is that your model is not good at detecting spam, right? It only captures 66% of the spam. So there is one explanation for that, and that's because this is an unbalanced, this is an imbalanced data set. It means that the classes are not represented equally. So here you have way more non-spam emails than spam emails. So, right, like 90%, almost 90% is spam, and less than 10% is spam. So this is very common. Some problems are like this in real life. It's not about data collection. That's just the nature of the problem. So you have very few observations for one class and a lot of for the other classes. For example, if students dropping, from school, like most of the students will keep on track, right? But there is a percentage of students that will drop at some point. So that's a problem that, you will face a similar issue under that context. Okay, so this is a summary of the metrics. So the recall, the idea here is out of all the actual positive cases, or the ones, right? How many did the model find? So it measured the frequency, like how good, the quantity. And instead, the precision focuses on the quality. So when the model says yes or when the model says positive or one, how often is it correct? So precision is about trust, quality of your model, and recall is about coverage, like how many are correct. All right. So there are different tools to kind of like find the threshold. Remember that we need a threshold to evaluate the probability, which is the output of the classification model, to be able to find y hat. So one of these tools is the ROC plots or curves. This ROC curve is very helpful to find good thresholds, because the threshold is not always 0.5. It depends on the problem, but it's not always 0.5. It depends on the problem. So let me give you an idea of how this ROC curve works. So in the y-axis, we have the sensitivity. The sensitivity of the recall for the positive cases, sensitivity. In the x-axis, we have 1 minus specificity. 1 minus specificity. So that means that in the y-axis, we want to be, high up, right? It means high sensitivity. That's good, right? High recall for the positive cases. And in the case of the x-axis, we want to be to the left, right? Because it's 1 minus the specificity. So you want to be close to the 0 here. So the perfect classifier is this one, right? 0.01. This means sensitivity equal to 1 and specificity equal to 1. That's the perfect classifier. A random classifier is this diagonal, right, which is far from the perfect classifier. And the idea, each point in this plot is for a given threshold, like let's say 0.1 or 0.2, you compute the confusion matrix, and then with the confusion matrix, you get sensitivity and specificity. We will solve an example. I will make a video with a walkthrough, an example of how to create the confusion matrix, and how to find the different metrics order. Now, the idea of the ROC plot or ROC curve is to get a point or get a model or get a threshold where the sensitivity and 1 minus the specificity is close to a perfect classifier. So we want to minimize this distance, right? We want to minimize this distance. Now, how do you know if your model is good or not? There are multiple ways. There are different metrics. So in general, you want a curve that looks like this, that is close to a perfect classifier, right? And there are some metrics for this. If you notice here, the height, the maximum height is 1, and the base here is 1, right? So the maximum area that you can get here from this rectangle is 1. So you can measure the area under the curve of these ROC curves. That's what we call the AU symmetric, right? Which is going to be between 0 and 1. So the the higher the AUC, typically if it's greater than 0.8, that's good. That's good from 0.8 and above. That's a good model or close to that. All right. So in addition to the AutoSecure, we also have the precision and recall plot, which is a little bit less popular than the previous one. Typically, when you are using binary classification, you will use the AutoSecure. But the precision recall plot is also useful because it shows you the trade-off of the precision and the recall. Now here, the best model is going to be close, or the ideal model is going to be close to the top right corner, It's different, because in the previous plot, in the AutoSecure, we are looking for top left, right? But here is top right. So here we have, again, in the x-axis, the recall. Remember, the quantity is a percentage, and the precision, the quality of the model, right? How much you can trust the outputs, those probabilities. So in this plot, you can find also a threshold that will find you a good balance between precision and recall. We want both of them, to be high for every single class. That's really important. Okay, so let's conclude. Remember, classification problem. A classification problem is when you want to predict a categorical outcome, one or more categorical outcomes using some features, right? There are multiple algorithms. In this video, we talk about logistic regression, which is a common baseline model that you will use for your comparisons. It has also high interpretability. That's important. So when you're doing machine learning, it's not just about like predictions with good accuracy. You also want interpretability. That means that the person that is using the model is going to be able to make decisions about the variables, like which variables are more important and things like that. So that interpretability. So the model evaluation should go beyond accuracy. Accuracy, you got to be careful because it can be misleading. Remember the problem about the fraud detection when your data sets unbalanced, then the accuracy is not a good metric. You need to check how good is the model per class, for each class. The AutoSecures and the precision recall curves, both of them are really useful to find, a good threshold that is gonna give you good performance. So now I'm gonna finish this video, but I'll see you in the walkthrough of the logistic regression problem. See you in our next session.